Okay, so now we will be doing DFS traversal. Um, these are the standard traversals of a graph, be it DFS or BFS. So in this case, we will be learning how to do DFS. Right. So for example, we have this case 0, 1, 2, 3, 4. 0, then 2, 1, 4, 3. 0, 2, 1, let's say 3, let's say 4. Although 4 was there, let's just okay. 4 and 3. So 4 is over here, 3 is over here. Okay. So how do we do a DFS on this one? So you can choose any um, node as your starting point, but in this case, I'm starting with 0. And I start from here. So first of all, the first thing that you have to do is create an adjacency list. This will most probably be given to you, but what does this mean? Basically, you have to store in a vector of vector all the nodes corresponding to basically neighboring nodes of a particular node. So how you will map them? So basically, say we have um, 5 nodes in this case, right? So what we will do is we will create a array, an array of 6 elements. So this will be 0, 1, 3, 4, 5, 6. Okay. So in this case, okay, you do not need to add six. So you can like have six indexes, which starts from zero because this is like a zero indexed graph. So you can check whether the graph is zero indexed or one index. So if it is one index, you can take like one extra index. But in this case, we have it as zero index, so we will map it using this. Okay, let me just. Okay, so in this case, let me draw this vertically. So 1, 2, 3, 4, 5, 6. This is 0, 1, 2, 3, 4, 5. Okay. So corresponding to 0, we have 2 and 1. 2 and 1 are the neighboring nodes of 0. So in the adjacency matrix, we have 2 and 1 corresponding to 0. And to 2, we have 0 and 4. So 0 and 4 over here. For 1, we only have 0. And for 3, we only have 0. For 4, we have only 2, 4, 5. Okay, we do not have a 5 here, so the fifth one is not needed. So we require 5 indexes in total. Okay, so this is like the adjacency matrix for this graph. What we will do next is simply go to its, so start from here. Okay, so we will keep track of the nodes that we have visited, because we, so in this case you will not encounter a cycle, but we might encounter some cycle which can uh, which will result in a loop like situation where we are like moving in the graph itself indefinitely. And what we will do to remove that possibility is just create a visited array with the same uh, number of indexes, not the fifth one. Um, so first of all, I have visited to 0, so I will mark this as 1. Initially, there will be 0. I'm not marking because I'll have to raise it then. So the first one is visited now. Now I will go into the adjacency matrix of this corresponding to this node, which is 2 and 1. So I will go to 2. I can go to either 2, 1 or 2. So in this case, I go to 2. From here, I go to 2, and I'll mark 2 as visited, and from that I can check the adjacency matrix of um, 0 and 4 are the nodes neighboring to as the neighbor nodes of 2. So 0 I can check is already visited, so I will not visit this again, but 4 is something that I will visit again, and hence I will go here. And from here, if I look at 4, the only adjacency um, adjacent node, or the neighbor of 4 is 2, which is already visited. So you will not do anything in this case. You will return from here. You will come here, and from here you will see if there is like any other node corresponding to this. So for 2, we had already visited 0, we currently visited 4, and there is no other node, so we will go back to 0. Now for 0 we will see if there is any other. There is 1, and there is also 3. And now we can traverse 3 or 1, doesn't matter. So we will traverse 1 first. So we'll go to here. And also at each level we will be storing the nodes that we are visiting. So first 0, then 2, then 4, and now we are moving to 1. Okay. And corresponding to 1, we have 0, which is already visited. So we will come back from here because we do not have any other node on 1. For 0 we have one another other node, which is 3. Now we will move to 3, and we can add 3 over here. So 3 corresponding to 3, we have 0, which is like already visited. So this in like in this way the DFS traversal is complete for this tree, and the DFS answer is 02413, which is the correct output. Let's move on to the next one, which is 102. First of all, a triangle, in the sense that a cycle in the graph language. Uh, so we'll have 102, 1 would be here, 0 would be here, 2 would be here. Okay, and we have 3 and 4 of also. 3 is here, 4 is here. So I can choose any of them, but for making this easy, let's start with 0, and let's create an adjacency list for this. This will require 5 indexes. Okay, so 1, 2, 3, 4, 5. Okay, 0, 1, 2, 3, 4. So for corresponding to 0 we have 1 and 2, and corresponding to 1 we have 2 and 0. Corresponding to 3 we no, corresponding to 2 we have 1, 0, 3, 4, 1, 0, 3, 4. Corresponding to 3 we have 2 only, and corresponding to 4 we have 2 only. Now we will start from 0. The 0 has corresponding to neighboring nodes, which is like 1 and 2. Now we can go to either one or 2. We'll go to 1 first. So if I move from here to 1, I'll check the adjacency for 1. It is 2 and 0. Also the visited array will be here: 0, 1, 2, 3, 4. And the traversal, I started from 0, I have moved to 1 now. And now this is marked as visited, this is also marked as visited. Now the next thing that we'll do is we'll check the neighbors of 1. Neighbors of 1 are 2 and 0. We have not visited 0, we have sorry, we have not visited 2, but we have visited 0. So I'll ignore this one. And for 2, I'll go to 2 now. Okay. Now the 2 is marked as, 2 is marked as visited. And from 2, I check the adjacency list. 0 has been visited, 1 has been visited. The only ones remaining are 3 and 4. We can go to either 3 or 4. Now let's go to 3 first. And in that way I will be visiting 3 also. So now I can go back from here, because there are no adjacency neighbors to 2, which are like 33, which are not visited. So I'll go back, and from here I will go check the adjacency for 2. These 3 are done, only the 4th one is remaining. So I'll go to 4 now, and corresponding to 4, the one is already visited, and hence we will not do anything, we'll go back. So from 3 we went to 4, then we got back, and the only one remaining here was 0, but that was also visited, so we will not go there. So this is the DFS 10123 4. Correct. This can vary slightly sometimes, but in this case it is not varying. um, the time complexity, as you can see in this graph, what we are doing is essentially going to each node, and for each node going to its adjacent neighbors, right? So the time complexity will be O of n plus of E in the sense that we are visiting each edge. So basically the degree, so which is like 2 into the edge for the traversal on each node. So this is like the time complexity, and the space complexity will be O of n, which is like, so not just for like the time complexity if we do not consider the adjacency vector, because this is like usually given to us. Otherwise this will make the space complexity as O of n square. But if we do not consider this, the space complexity will be O of n, because of the visited array and the DFS factor that we will use to store it. And also um the recursion stack space. So in the case of a skewed graph, when all the nodes are like stacked in one line, so in that case it will be O of n, because we'll be going to all the nodes. um yep, so let's code this one. Now for code, we will first of all require the DFS vector where we will be storing the value. So let's try to code this vector int the DFS array, or let's call it DFS v. Okay, and I will not initialize it with anything. I'll just have an empty vector for now. Now I'll have a DFS callback. I will also need a visited array to keep track of the nodes that I am visiting or that I have visited already. So another vector, this will be called as visited, and this will have the same size as the original adjacency vector, because that would basically mean all the nodes, and initialize it with 0. Okay, now we have visited array, we have the vector. What we need is a start. Let's start with 0. So the start will be 0. uh, we will pass the adjacency vector. We will also pass the visited. Okay, my bad. Okay, so adjacency is passed, visited, and DFS vector. And after everything is complete, just return the DFS vector. Okay, now since we do not want to create like a copy every time, I'll just make changes to the reference, so we'll have more accurate result. Okay, so let's do a void DFS such that first of all we'll need the starting node. So int start, and let's take that adjacency vector. This is like an ideal case. Sometimes you'll also have to like create this. You can simply do that by like checking neighbors of each node and storing them in the vector of vector. Okay, now the next thing that we need is the visited array. So let's take it up from here. Let's pass all of them as a reference instead of a copy. So let's paste this over here. This will be a reference. This will be a reference. Okay, now let's do the real magic. So the first thing that we will be doing in this case is marking the current node, which is like the start node, as visited. So we will do this for each recursion call that we will be calling. So in the visited array for this start node, just mark it as visited because we have visited now, and put this into the DFS vector that we are creating, saving the traversal. So push back the start. Okay, and now let's do a for loop. Not really. Okay, let's do a for loop, traverse over that adjacency list and go through all the neighbors of that particular node. So auto x of adjacency of the start node, and this will give us all the neighboring nodes of this particular node. And we'll first of all check if we have already visited this or not. um, so if we, not this but like X, have we visited the neighbor of this start node? No. If no, then we'll do a DFS for that. First thing is the node is X in this case. Second thing is adjacency list, we'll pass adjacency list. Third thing is the visited array. We do not have to worry because all of them are being passed as a reference, so we'll not lose any changes. So I think we are checking if they're like if that node is visited or not. We are doing a DFS call for that. We are visiting every time, and we're pushing also. So at after like everything is finished, we should have something in the DFS vector. I don't see any issue at this point, but okay, there is an error. DFS of graph, DFS week. Okay, so the adjacency size. Okay, so what we did was basically, I think we removed it, right? I think while copying we made some error. Uh, is there any issue here? Hmm. This was what? This is 56 first line. This is private. This is void. This is ending over here. We have commas at right places. This is starting from here. This is ending over here. If condition for loop. Right, if I'm not wrong, if I do this, this is the for loop, and that is the outer loop. I don't see any issue. Is there an issue? Is there an issue? Is there an issue? Where am I getting the error? I'm getting the error at expected. Let's just try to reset this because I think I have lost. But this was it, right? I don't see any changes. This is a private solution. This is a DFS call. The first one is a start. Second one is the list, adjacency list, which is the same as this one. Visited is integer vector, which has been initialized to 0 with that size. And the last is also vector with reference DSVV expected at the end of the input. Are we missing something over here? Okay, I think I do know. So basically, I think a bracket is missing over here. Fuck. Okay, now this works. Let's see. Okay, yep, this worked like a charm. So this is the DFS traversal for so on each for each node we are like basically traversing through all its edges. So that is basically degree, which is 2 into e, hence the time complexity of n plus O of 2 into h, and the space complexity as we discussed in the worst case for skewed graph O of n, and also because we have O of n visited array and the answer array also. So this is like the basic DFS traversal, which is very helpful in the graph questions. Thank you.